Ladies and gentlemen, my welcome everybody in our extraordinary Wigner colloquium. Our guest and the visit of our guest is connected to the myography conference last week, organized by Laszlo Olach and the myography group of RMI. And my pleasure to welcome Professor Morishima Kunihiro from Nagoya University in Japan, who is visiting the seminar with his 3 colleagues and co-workers. And actually, his CV is very simple because he was educated and worked at the Nagoya University, as far as I know, continuously, and where now he's an associate professor of the leading expert of the Muon laboratory.
Yes. Yes.
He was working at the Opera neutrino experiment and also using the technology of emulsion detectors for myography, so for muon detecting. And he is famous about muon archaeology or archaeological connection. And especially, as you see, the most famous work is the investigation and research of several pyramids in Egypt, especially the Cheops pyramid, where the new chamber was discovered, but we will see soon where and how and what else could we learn about myography and muons using for archaeological and earth science and geophysical research in general. So you are welcome in Wigner Institute, and please, the floor is yours.
Okay, thank you. Thank you for introducing me. So I'm Kunihiro Morishima. I'm from Nagoya University. So thank you for inviting me to talk in this seminar. So today I will explain. I will talk about the cosmic ray muon imaging with nuclear emulsions. So I will explain the emulsion technology and application for cosmic ray imaging. So the cosmic ray muon imaging is a non-destructive visualization technique. So this animation shows the cosmic rays. So the primary cosmic rays, main component of primary cosmic rays are protons. So protons interact with the atoms in the atmosphere like this. And then secondary particles are produced by the interactions. So secondary cosmic rays includes pions. So pions decay into neutrinos and muons. So like this. So interaction point is here. So the cosmic ray muon imaging uses high energy cosmic ray muons that naturally reach the Earth's surface. So these techniques allow us to investigate the internal density distribution and the structure of large-scale objects and geological bodies. So the cosmic ray muons have high penetrating power, so they can pass through the thick objects. So for example, X-ray cannot penetrate more than 1 meter thick materials, but cosmic ray muons can penetrate more than several kilometer rocks because several muons have a very high energy. Therefore, muon imaging can provide internal information that it is difficult to obtain with conventional methods such as X-ray imaging. So the energy required for a muon to pass through the target depends on the path length and materials, like this. So path length is here. So in the case of the same incoming directions, shorter or less dense paths allow more muon to pass through. So here is the path length is larger than here. So more muons pass through to the detectors. So cosmic ray muons arrive from many directions. So 3D angle measurement is essential to estimate their path. So like this. So by measuring the angular distribution of transmitted muons, we can estimate the integrated density along each path inside the target. So the 3D detector are essential for the cosmic ray muon imaging. So there are three types of detectors for cosmic ray muon imaging. So this picture shows the detectors used in the scan pyramid project. So I'll explain scan pyramid project later. So the nuclear immersion and plastic scintillator gaseous detector are main detector are used in for muon imaging. So we are developing and using the nuclear emulsions for cosmic ray muon imaging. So these detectors has different advantage, but major differences are from nuclear emulsions. So the main differences is real-time measurement. So nuclear emulsion cannot acquire and analyze data in real time. However, nuclear immersion has several advantages that compensate for this limitation. So I'll explain the nuclear immersion. So nuclear immersion is a photographic film type detector which can detect the charged particle in 3 dimensions. So this shows the nuclear immersion after chemical development. So it looks like transparent films. So this shows a cross section in 3 dimension. So the detection part of the nuclear emulsion is coated on both sides of transparent plastic films. So the thickness of the layer is about 80 microns. And the sensitive, there are many small silver bromide crystals dispersed in the gelatin layer. So silver bromide crystal is sensitive to the charged particles. The size of the crystal is about 0.2 micron or 0.4 microns. So this is very small crystal. So thanks to the small crystal size, so we can detect the trajectory of the charged particle in 3 dimensions with the accuracy of less than 1 microns. And the thickness is 80 micron, and the crystal size is less than 1 micron. So the trajectory is visualized in 3 dimensions. So after chemical development, so we can confirm the trajectory of the charged particle by the chain of silver grains. So this shows a optical microscopic image of the tracks recorded in the emulsion. So this is a very high precision, but we need to use the optical microscope. So the nuclear emulsion has important features. So first is angular measurement accuracy of mid-region obtained from submicron position accuracy in 3 dimensions. And second, in principle, it is possible to measure in all directions. So third, the no power supply is required, and lightweight, and thin, and very compact. And the package is highly waterproof and dustproof. So this is a nuclear emulsion detector. So this is a real detector. So this is packed by the aluminated package. So you can see that this is very light and compact and very flexible. So these features make it easy to carry and install in any locations. And also it is easy to manufacture in large quantities. So which make it possible to realize large area detectors and to set up detectors at the same time to observe a single object from multiple directions. So now we are developing and producing nuclear emulsions at Nagoya University by ourselves. So, this is emulsion gel, and this is crystal produced by our system. So this shows our emulsion production machine. So now 3 production machine for different scales are in operation. So by using small scale machine, we can produce 1 kilogram emulsion gel. So this is corresponding to the 0.3 square meter emulsion area. So this is used for the R&D experiment. And the second is a medium scale machine. So this machine can produce 1 square meter emulsion. So this is used for the pilot testing. And the third is the largest scale machine, so which can produce the 10 square meter emulsion area. So this is used for the manufacturing. So by using these systems, so maximum production capacity is about 1,000 square meter per hour. So assuming 150 days of operation. So we have a very good facilities at Nagoya University. Sorry? How much is sell? I didn't I I didn't say a price? Price. So very very expensive. Yeah. So now so silver price is very increasing. So, okay. So I'll show you the production of the nuclear emulsions. Oh, sorry. So this is a emulsion gel. So this is hotted. So the emulsion gel is liquid. So by adding the chemical compound to the emulsion gel, we can control the detection efficiency and stability and reduction of noise. And by using this emulsion gel, we make the emulsion by coating the emulsion gel onto a plastic base. So this is emulsion gel. So we should work in the dark room like this. So this is emulsion gel. So after drying, we can cut emulsion and we can make the suitable size. So the 4 thick base films, such as 500 microns, so manual coating is required. So I explained before. The maximum production speed is about 300 square meter per year. So, but for thin sheets such as 200 micron thick base, so a roll-to-roll coating system is developed and in operation to increase the production speed. So this shows a roll-to-roll machine. So you can see the very thin base. So it is easy to roll it. Although the emulsion layer thickness is limited, so this system achieves about 1,000 square meter per year. So, but the performance depends on the thickness of the base. So a thicker base improves angular accuracy, and the thicker emulsion layer improves the signal to noise ratio. So we are choosing which methods uses for each purpose. And I explained the nuclear immersion scanning system called HTS, Hypertrack Selector. So this movie, oh, okay, can you, okay. So this is a nuclear, this is a scanning system. So, so the blue light is illumination light. And metallic cylinder is an objective lens. So nuclear immersion is stored, is fixed here. But immersion is transparent, so it is difficult to see. And we are mounting the 72 sensors around here and here and here. So to increase the scanning speed, so the field of view is very large, about 5 millimeter by 5 millimeter. So to image this wide field of view, so a total of 72 sensors are used. And every sensors readout of every sensors are connected to the GPU in 72 personal computers. So by using these systems, we can recognize track by track in real time, like this. So this is a computer view. And so there are many computers to reconstruct the tracks in emulsion in real time. So total 36 machines. So this is a world highest scanning speed system in the world. So the principle of track recognition. So by using this system, so we took the tomographic images of an emulsion layer. So emulsion layer are taken by moving the objective lens along the optical axis like this. So by using this method, we can take the image of each track. The acquisition images are processed by binarization and image alignment and have transform like straight line recognition. So through this process, the three-dimensional position and angle of each track are reconstructed like this. The position and angle accuracy depends on the track angles. So for tracks perpendicular to the nuclear emulsion, the accuracy is about 0.3 micron in position and 2 or 3 meridian in angle. So by using this system, so we can achieve the very precise performance. So I shown before the scanning system. So that is the first system of HTS. So the scanning speed of HTS1 is about 0.4046 square meter per hour, like this. So this is the first system. So now we are using the new system called HTS2. So HTS2 entered the full-scale operation for Muon imaging application 1 year ago. So this is HTS2. So you can see the very big objective lens. So HTS2 achieve a speed of up to 0.9 square meter per hour by using lower magnification lens and a wider field of view than HTS1. So the scanning speed of HTS2 is 2 times faster than that of HTS1. So by using these systems, so we achieve the maximum scanning speed is about 500 square meter per year. So, but this scanning speed is not enough for the is lower than the production speed of nuclear emulsions. And also, so these systems are used for not only muon imaging, but also neutrino experiment and balloon experiment for gamma ray, for detection of gamma ray source. So our system, this system is very high, achieves a very high scanning speed, but not enough for all experiments. So now we are developing the next generation system called HTS3. So HTS3 aim to achieve up to a 4-fold speed increasing over HTS2. And so in our plan, So we will make the half-scale operation in 2 years. So this shows a HS3 conceptual design. So while HS1 and 2 are single lens system, but the HS3 use multi-lenses. So here is a lens area. So this is a lens and sensor. So HS3 achieve higher speed by maintaining the same magnification as HS2. So while expanding the single field of view through the use of high resolution sensor. So we are changing the sensor, new one. So so detailing design is in progress. So including the stage and lens alignment. So now we just started to construct this system. So I summarize the nuclear module technologies. So by using the analog film, we record the tracks. And by using the digital technology of automated scanning system, so we scanned and we reconstruct the three-dimensional tracks. So this combination enables measurement of various targets. So emulsion film is very suitable for usage in any area. So by using emulsion, so the field is spreading. And so now production and scanning speed is reaching several hundred square meter per year. So now we are developing the faster scanning system and higher performance nuclear emulsions. So I didn't explain details, but we can produce the emulsion gel by ourselves, so we can improve the performance of nuclear emulsions. So we are developing both sides of technologies. So I explain the brief history of cosmic imaging with nuclear emulsions. So first experiment was done by Professor Tanaka from Tokyo University and Nakano-san from Nagoya University. So they measure the volcano with nuclear emulsions. So when this measurement was conducted, so I was a PhD student at Nagoya University. So I am developing the previous scanning system called the SUTS for the Opera experiment here. So I know this volcano measurement, but I didn't analyze this data directly. So I can't explain precisely. So I will explain another measurement in this talk. So so first measurement is volcano, and next experiment is measurement of reactor, Fukushima Daiichi nuclear power plant, and then we measure the pyramid project. So reactor. So I'll explain the reactor and pyramid project in next slides. So I'm working. I start to work on the Muon imaging from the 2011 after I got a PhD thesis. So I read the reactor experiment and the pyramid experiment from 2011 to now. So the scanning system is changing from the 2007. So at the 2007, so previous system called HSE is used. And then so system is changed to HS2. And also nuclear immersion is changed. So at the so in 2007, so this time is before starting of Opera experiment. So the Opera experiment uses the machine to make the emulsion films made by Fujifilms. So the film is called opera films. But Fujifilm's film couldn't provide the emulsion films to us. So from 2010, we are developing we are learning the method of production of nuclear emulsions from the uh, retired researcher of Fujifilms. And now we are able to produce the nuclear emulsion by ourselves. So from 2010, so we use nuclear emulsions made by Nagoya University. So now, so we are expansion of the business target by using our scanning system and nuclear emulsions. So I will explain the Fukushima Daiichi nuclear power plant measurement. So the Fukushima Daiichi nuclear accident occurred on March 11, 2011, and the core meltdown was suspected. So at that time, the radiation level inside the reactor building was too high to enter, and there was no direct way to investigate the inside. So therefore, we proposed an internal investigation using Muon imaging in collaboration with Toshiba company. So we selected the nearby the turbine building as the detector location because the radiation level was relatively low. So this is a reactor building, and so this is a turbine building. So we installed in the turbine building. So this shows a reactor building and turbine building. So blue part shows a muon detector. So in the turbine building, so radioactivity is lower than main building, but a large number of gamma ray induced electrons accumulated in the nuclear emulsions and become serious noise. So it will be difficult to analyze and detect muon tracks. So to reduce this noise, the nuclear emulsion was placed inside a red box in the turbine buildings during the observation. So this is a red box. So we installed a 5 centimeter thick red shielding in the corridor in the turbine building and reduce the gamma ray dose to 1/3. So even with the shielding, so each observation period was limited to only 3 weeks, very short time. So the nuclear emulsion was replaced several times, and the data were analyzed. Data were accumulated and analyzed. So in 2015, we reported the result showing that meltdown has occurred. So I'll explain this result. So the upper figure shows the cross section, and the bottom shows the muon image. So the color indicates more material or less material. So storage pool, so in the storage pool, water and core, used core are stored in the pool. And so in the core region, so the amount of material is almost same as the storage pool. Should be almost the same material exists in the core region in the normal case. So, but by you can see the result. So in the core region, so there are less material than storage pool. So this is a direct measurement of the meltdown occurred in the Fukushima Daiichi nuclear power plant. So in the case of Unit 2, this is the first measurement. So by using the nuclear emulsion, so we achieve a very clear image of the meltdown. So your question is why? What is it? So we started to discuss with the Toshiba Corporation from 2020. So I proposed in 2011, but we discussed from 2012, and we conducted this measurement in 2014. So we analyzed in a year. Okay. So we need to prepare many things to conduct in the Fukushima. So let's move on to the Scamperium project. So this project is conducted from 2015, since 2015. So the mission of this project is to reveal the mystery of the pyramid by using state-of-art technologies, including the cosmic ray imaging. So this project is organized by the Egyptian Ministry of Antiquities and Cairo University. So the participation companies and institutes are described here. So Egypt and Japan, France and Canada and Germany. So the target pyramids are listed here. Sorry, here. So Bent Pyramid is conducted in 2015, and Kuf Pyramid was conducted from 2015, and so on. So the by using cosmic ray image, cosmic ray imaging is conducted by Nagoya University from Japan with nuclear emulsion, and KK by using plastic data from Japan, and CEA by using the gas detector from France. So in this talk, so I'll explain our result, only our result. So we installed our detector in two locations. So in the center. Sorry. So this shows the cross section of the Kuf pyramid. So the two rooms and one big corridors are connected with very narrow corridors. So the narrow corridor is the width and height is less than 1 meter. So we installed our detector in two places in 2015. So first position is here. So this room called Queen Chamber. So here is Queen Chamber. And the second position is here. This called the descending corridor. So this is descending corridor. So in the Queen Chamber, there are very large floor. So we use the large area detector. So in this room, so the detector area used to analyze is about 0.45 square meter. On the other hand, the descent corridor is a very narrow passage. So we use the 3 emulsion detector installed in and which is installed in this corridor. So this area is 0.1 square meter. So thanks to the nuclear emulsion property of nuclear emulsion, so we can install in the very narrow passage like this. So by analyzing this data, so we discovered two voids inside the pyramid. So first void named Scan Pyramid Big Void. So this is located in the center of the pyramid, just above the Grand Gallery. So this Grand Gallery is a very, very big, large volume corridor. So left shows the simulation image, and right shows the observation result. So the color indicates the Muon flux, high or low. So the high means less material, and low means large materials. So so you can see the top pictures, simulation and observation. So you can see the differences between two images. So in the right panel, so as indicated by the red arrows, so you can see the differences between differences against the simulation. So the mu so this region this mu flux this region means mu excess against the simulation. So simulation is done by using the 3D model, including the known structure inside the pyramid. So the differences are detected. So that is a new discovery. So this is a very big void. So because so this light, so this image corresponds to this grand gallery, and the mu excess is almost the same as the image from grand gallery, image of grand gallery. So the discovered void is almost same volume as grand gallery. And second discovery is corridor-like space just behind the nose face. So left shows the simulation and right observation. So you can see the muon excess in the right panel. So this here corresponds to the narrow corridor discovered by our measurement. So this corridor called the scan pyramid nose face corridor. So I'll show you the recent progress on scan pyramid nose face corridor. So we detected the muon excess in the descending corridor in 2016, but at that time we didn't decide the precise three-dimensional structures. So we installed nuclear emulsion detectors in mulch locations from descending corridor and the album corridors. So album corridor is used for the tourist route. So it is difficult to install the detectors. But okay, yes. So from the descent corridor, so we can see like this. And from album corridor, so we can see like this from other directions. So album corridor is difficult. It is difficult to measure from the album corridor. But so thanks to the compactness of emulsion, so we can install the very small cave on the aluminum corridor like this. So this is emulsion. So one emulsion. So emulsion size is very compact. So the successful measurement were performed in an environment where other detector would have difficult operating. So the position and size of the discovered space. So next. So this is the observation result from 6 positions. So top panel shows the aluminum corridor result and the bottom are descending corridor result. You can see the clear muon excess from the corridor. So the position and the size of the discovered space were estimated with 10 centimeter accuracy by a chi-square test, assuming a cubic structure. So using measurement from 6 directions like this. So based on muon imaging result, so this is a result of our measurement. So structure is width is about 2 meter and height about 2 meter and length is about 9 meter. So based on the muon imaging result, the existence of the space was confirmed by using optical fiber scopes. So this is a movie of the confirmation by using optical microscopes. So this was conducted in 2023. So this is a fiberscope image. And so this is a hidden void in the pyramid. So this room was discovered by our measurement. So this structure. So this is a fiber image, and this shows the north face of the pyramid. So the discovered corridor-like space has a roof, and this roof corresponds to the upper part of the roof. So this chamber, this corridor-like space was very clear. So the internal structure of the was three-dimensionally reconstructed by photogrammetry using fiberscope image and LiDAR survey result. So this is a result. And so this is a movie of the three-dimensional model of the internal space. So we can see by using this model, we can walk in the corridor by using the VR. So this is very interesting. So now, archaeologists are discussing this corridor. What is the purpose of the corridor? And then, so the three view drawing of the SPNFC was made, and the size of the corridor measured by photogrammetry. So here shows the photogrammetry result and the myography result. So the reconstructed result shows a good agreement with the Muon imaging result and the photogrammetry result. So it is a very interesting result, very interesting. So by through this measurement, we confirm the estimation accuracy of Muon imaging is very precise. So in the scan pyramid, so we add, in addition to these locations, more than 20 nuclear emulsion plates of various size and configurations were installed at many sites inside the Cliff pyramid. And so, for example, so in the grand gallery we installed, and also in the top of so this is king chamber. So above the king chamber, very narrow space exists. So we installed, and also so underground chamber we installed. So we are using several detectors. So the analysis is not finished. So analysis is still ongoing. So because of very huge data we have. So and the three major pyramids of Giza. So I explained the Khufu pyramid, but we started to measure the Khafra and Menkaura pyramid. So I explained the observation of pyramid of Khafra. So nuclear module detector were installed at the same location in Belzoni chamber as those used by Alvare. So Alvare already measured Khafra pyramid to search for the hidden structure. So he conducted the experiment about 40 years before. So this is Alvarez's result. So they claim there are no hidden structure inside the pyramid, Khafra pyramid. But we want to try again to search for the hidden structure inside this pyramid. So we installed the emulsion detector area of 2.25 square meter, and we achieved the 70 million Muon tracks. So, and also we sorry. So this is a spark chamber by using Albare, and this is a nuclear emulsion. So both picture is the same position, same location in the chamber. So so now, so additional nuclear immersion detector were installed at other locations in the Bellton chamber. And large area detectors and inclined detectors here, inclined detectors have been deployed at the multiple sites and observation are ongoing. So measurements are also being carried out beyond the observation region covered by Albare to search for previous unknown internal structures. And also we started to conduct the measurement in the Menkara pyramid. So cosmic ray muon imaging for archaeology are conducted. We are conducting the cosmic ray muon imaging for archaeology. So I already explained the pyramid, but we are measuring the at many parts in the world. So first I explained the temple pyramid of the Maya civilization in Honduras. So this is Temple 11. This pyramid called Temple 11. So now we are searching for hidden structure inside the pyramid. So in the case of Temple 11, so there are many passages in the pyramid for the investigation. So in this picture, like this picture, so we installed the nuclear immersion and to search for the hidden structure. So for example, this is one of the result. So for example, so this is a region of interest, but we didn't detect the signal from the hidden structure. So now we are continuing this project. And also we conducted the muon imaging in the underground at Naples in Italy. So this shows a top view of the Naples urban area. So underground, there are complex structure. So this shows a 3D model of the underground structure. So we installed the nuclear immersion in the bottom part of the structure like this. So this shows the observation result. So this shows a muon flux excess. So the red color shows the void. So each void corresponds to these 3D models. So by checking the correspondence, so we found the muon excess around here. So in this picture, so we show one image, but we measured from two positions. So both positions we observed the muon excess. So by reconstructing the three-dimensional positions, so the void exists in the underground. So this is we confirmed the unknown void by cosmic ray muon imaging. So this is this should be the so this discovery is possibly a Gaussian period Boolean chamber. And so in this picture, so we can see the very lower muon flux region. For example, here and here. So horizontal structure and vertical structure. So this corresponds to the wall of the building. So you can see this building. So here is a wall and wall, a horizontal and vertical wall. You can see. So each walls correspond to this panel, this muon, less muon regions. So this shows the muon imaging with nuclear immersion provides a very high precise image. So nuclear immersion muon imaging is suitable for the underground investigation. So now we are spreading the targets of the Muon imaging by using nuclear emulsion. So this is a list of our interests. So first, I'll explain the underground explanation using myography. So underground cavity investigation is very important in Japan. So because in recent years, road collapse caused by sealed tunnel construction and aging infrastructure, such as sewer pipes, so have become a serious issue in Japan. For example, this upper picture shows a sealed tunnel construction and bottom pipe damage. So it is important to understand the underground cavities and aging infrastructure. So, but the conventional methods have limitations. So therefore, a new explanation is required. So we are planning to use nuclear emulsion to search for the hidden void underground. So to install detectors underground, it is essential to use the existing cavity or insert detectors into the boreholes. So like this. So if cavity exists in underground, so we need to install the detector just just under the cavity. So if there is a pipe, we can install our detector like this, but if there is no space, we need to make a borehole. So now we are developing the borehole detector. So this shows our detector. So the borehole detector can be inserted into the borehole with a diameter of 10 centimeters or less. So nuclear emulsion film with width of 4 or 5 centimeters and the length of 30 or 40 centimeters are fixed inside the stainless steel pipe with a diameter of 7 centimeters. So here is the nuclear emulsions. And also orientation sensor is installed in the pipe. The total detector length is 1 or 2 meters we produced, and the weight is about 15 kilograms. So nuclear emulsion can be made compact without losing its high accuracy. So even at this size, it provides an angular resolution of several milliregion. So probably the highest resolution among the borehole detectors. So this is a significant advantage because resolution is essential for imaging. So a demonstration test was conducted at the site in Japan. The direction in which a high muon flux was observed was checked by borehole investigation, and the results shown good agreement. So today, so I can't present the result, but we have a positive result. So further challenges including the improvement of waterproof performance and ensure the flatness of the nuclear emulsion films. So an improved new detector is under development. So this is a picture. So, and also we are applying our technology to the old development. So the measurement currently being conducted at Kamaishi mine in Japan. So it is a skarn type iron ore deposit, and large scale mining has already ended. So the site is currently operated mainly for a water-related business and underground space utilizations. So detectors were installed at the depths of 200 meter and 1500 meter for observation. So large area detectors are essential for this measurement because the muon flux is very low. So we prepared up to 2.25 square meter detector. So like this. So this size is compatible in the scale that used in the pyramid observation. So 4 months of stable continuous observation were carried out in a low temperature environment. So we so now analysis is currently ongoing, but we observed the tunnel and mined out cavities in our result. So it is also I cannot present now. And we applied our detector to levee inspection. So in recent years, so intense rainfall and flood disasters have become a growth concern due to the climate changes. So in Japan, steep terrain often causes rapid rise in river water levels. So therefore, the importance of flood control infrastructure, such as river, is increasing. So river levee soil structure and water seepage can create cavities or weak zone inside them. So these internal defections may be detected as density differences. However, it is difficult to obtain the internal density information of levees non-describability using conventional methods. So since 2022, we have been developing this technique for a river levee in Niigata. So nuclear immersion detector were installed inside the pipe like this. So we made a system was designed to install and install and collect a nuclear immersion detector respectively at the same locations. So so in the measurement, so we successfully so it is difficult to see the differences, but we successfully detected the 1 cubic void in the levee. So the area is indicated by the arrow. But so this is raw data. So this is before collection of the efficiency. So it is difficult, but we confirmed. So here correspond to here. So just under this metal plate, there is a 1 square meter cavities. So this is a good result. So now we have a plan to shorten the measurement time by increasing the detector size and improvement water performance and conduct the measurement from outside of the levee. And so we are applying the tree diagnostics. So Japan has many large trees, and all the trees are important as scared trees and cultural assets. So internal cavities and decay are difficult to identify from the outside, but they can increase the risk of tree collapse. So for trees with this diameter of several meters, so internal diagnostics is difficult using conventional methods. So we are using the Muon imaging to investigate the internal structure of the tree. So we conducted, our target is Benkei cedar at Gifu Prefecture in Japan. So in October 2017, a typhoon caused damage, including a breakage of a branch at the top of the tree. So internal decay caused by wood decay fungi is possible, raising concerns about cavity formation inside the main trunk. So visual diagnosis has been conducted by three doctors, but conventional method cannot determine where internal cavity exists or not. So we use the compact detector here. So we designed compact detector, and this design allow installation without disturbing the landscape. So this is a very large tree. So we try to see inside the cavity. So this is the result. So left top shows the simulation without void. So this dashed line shows the edge of the tree. So here is the shadow of the tree. And bottom shows the simulation with the void. Diameter is about 2 meters. So you can see the differences between the shadow of the tree. So left shows the measurement. So this shows the measurement result. So you can see this measurement is almost the same as the simulation. So this tree has a very large void. So this shows the cross section. So you can see a very clear Muon XS simulation. Green line shows the simulation and red line shows the measurement. So this is very compatible. So this void fraction of the tree is 44%. So I think this is a very big void. So, and also, I explained the volcano experiment. So we conducted a measurement at Omureyama, Shizuoka, in Japan. So we use the nuclear emulsion, 10 nuclear emulsion detectors. So these detectors are installed in the underground. So this is compact, so uh, we can install underground. So from 10 detectors, we reconstruct the Muon flux and we reconstruct the three-dimensional density distribution. So here is the result. So red color shows the higher density region. So this corresponds to the cold magma passage. So this is very important, a very interesting result. So now we have a plan to our detector to measure the mountain in Hokkaido. And for example, this is a bridge application. So this shows a bridge, so with three holes. So we installed our detectors just under the bridge like this. So in total, 21 detectors. So from this result, we will try to reconstruct a three-dimensional image. But anyway, so from one detector, we can see the clear cavities like this. This you can see the three lines. Three lines correspond to three holes. So this is very precise image. So so by using nuclear emulsions, so we can use the detector underwater. So this is a test case. So this measurement aim is to measure the muon energy spectrum in low energy regions. So for this is so one panel is one emulsion detectors. So for example, so vertical direction and horizontal direction we placed. So from vertical direction, so we can see the from 90 to 40 degrees. And from vertical detector, we can measure the 45 degree to 0 degree. So by using both detector, we can cover all directions. So this big structure is installed in the installed underwater. So top of the detector is not underwater, but the other detectors are underwater. The thickness of the water is different in each position, so we can measure we can set the energy threshold in each detector. So by using this result, we can measure the muon energy spectrum in low energy regions in several angles. So this is summary. So using the high penetrating power of cosmic muons to see through the artificial and natural structures. So by using so we are using the nuclear emulsions to these technologies. So so this enables measurements in narrow, nuclear emulsion enables measurements in narrow spaces, such as the borehole and even in submerged environments. So we discovered an unknown cavity in the pyramid of Khufu, and we are planning to spread towards social implementation. So now we are conducting a demonstration test for underground cavity survey and civil engineering structure inspection and underground resource exploration and so on. So that's all. Thank you so much.
Thank you. Are there any questions? Yeah.
I wonder whether you can give me a more precise answer than very expensive. Can you tell me in yen per square meter or per square meter the costs of this detector?
Cost?
Cost?
Cost, also, it's difficult to answer. But so not only emulsion films, but also scanning system. Not only emulsion film, but also scanning system. So scanning system is very expensive, more than, yeah, very expensive.
I expect the expertise is also expensive.
Sorry?
Is using the whole setup and the expertise to calibrate and giving the proper answers is also expensive. Modeling the environment first.
Model environment.
It's huge. Yeah, for example, the pre-image of the tree, modeling the tree could be a tricky subject, is it?
Tree?
Yeah,
Tree.
for example, how many persons performed, established or developed this model?
So you are saying about the tree, not only tree, but also.
Not only tree, but so this is not only just put the detector and scan, but also you need the model and compare to the.
So yeah, very, very many things. So for example, we need to minimum 2 or 3 persons to install the detector. And we need to produce the emulsion films, and we need to develop the emulsion films, and we need to scan the emulsion films. So many people are working on this project. So in our laboratory, so about 10 or more students are developing these techniques.
Any more questions?
I have a question. You mentioned on one of the slides how many particles you can detect per square meter or per layer, but what is the convenient limit? How many particles can you detect on one foil?
Okay. So
10 million or 100 million or how many?
So 10, 10, huh? 10,000 tracks per square centimeter. Yeah. Is safe for the analysis. Yeah.
Just a quick question. I mean, normally for X-ray image plate and things like that, after reading the information, you can clean it, reuse the system. Can you reuse it after your detector after analyzing or not?
No, I can't use. Yeah. One way. Yeah.
Are there any questions from the internet?
Yes. I am Deju.
Okay, just wait.
Raised my hand. So I hoped very much to hear about the opera experiment from you, because the opera experiment worked in Gran Sasso, detecting the direct oscillation of muon neutrinos coming from CERN to tau neutrinos, 5 such events, but it used a lot of emulsion plates. Now, I don't know, were you participating in this experiment?
In the opera experiment.
Yes.
Yeah.
Yeah.
So I can't catch your main question.
Okay, my question is the following. What was the advantage of using emulsion instead of fine grid chambers? Because it is okay, all the examples you brought in your discussion are all stable things. You are observing holes or deposits standing. Now, in the case of the opera experiment, you had the exact timing of the neutrino star, muon neutrino starting from CERN, and you lose this timing in the emulsion technique. What was the advantage of using it instead of chambers?
So in the neutrino experiment, so we need the timing information. So where which ECC is detecting which ECC detected the neutrino. So the opera experiment we need the additional electric detectors. For example, plastic scintillator. So in the case of Newton experiment, we need help from the other detector. But in the case of cosmic ray muon imaging, so we don't need so the almost case we don't need the timing information. So because if the target is changing in time, so we need time information. But so for example, pyramid, we don't need the time information. So we can use the emulsion, only emulsion detector.
Yes, of course. But in the case of opera, you could have used chambers instead of the emulsions.
So sorry, instead of emulsions.
Yes, you don't need, in the case of an accelerator experiment, you usually don't use emulsion technique because it doesn't give you the timing advantage. The emulsion is a cumulative method. You just put it there and wait. Now, in the case of an accelerator experiment, this loses the advantage of timing.
So, yes. Okay, I understand. What is advantage by using nuclear emulsion? Your question?
Yes, of course. That's what I told already 3 times. Yes.
Okay. Yeah. So I think so there are many advantages. For example, the very compact and lightweight. So we can install the emulsion in, for example, narrow passage or underwater. So, but I think the other detector is difficult to use, flexibly use.
But in the case of the opera experiment, it was several cubic meters of emulsions were used. Cubic meters. Huge, really.
So in the opera experiment, so a huge amount of emulsions
Yes.
are used. Yes, you are right.
You see, that you cannot say it is small or compact or lightweight. It is a ton of emulsion was used in the opera experiment.
Yes.
May I comment to this? I'm also a Deja.
Yes.
The emulsion had an excessively good, incredibly good position resolution. Okay,
Yeah.
and they needed to pick up the tau, okay, which decayed, and they needed to image the actual tau decay, and that's why they needed the emulsion. They need a large volume, very precise position measurement, and that's why they need it. Okay, because it would have been only possible using semiconductor.
Yes.
Which was it was not possible to make it that large. Okay, this was huge detector. Opera was huge, and they had a very large detector, so emulsion was an extremely large volume with a very, very good precision, and they simply took out the brick which was hit.
Yeah, I know, but you see, I am just thinking about the LHC experiments where they have the same 10 to 100 micrometer resolution using semiconductor plates and layers of semiconductors. So it approaches the same resolution, but it is about a million times faster than the emulsion technique.
That's correct, but it's much, much smaller. So Opera was huge.
Yeah,
total
I know,
volume,
but
total sensitive
CMS,
volume.
the inside of CMS is just as large as Opera.
No. It's very,
No?
very tiny. It's much smaller.
Mm.
And also you're looking for vertex tracks, whereas Opera was looking for everywhere in the large volume. So it was
Okay, that's a big difference. Okay. Thanks. Sorry for the complicated question.
Thank you. One question more.
Thank you so much for this nice talk. I just want to know what kind of material you used in the emulsion.
So your question is a component of emulsion.
Yeah, composition of emulsion.
So the main component is silver bromide crystal. Silver bromide crystal dispersed in the gelatin layer. So main component is silver bromide crystal and gelatin.
Okay. And when the particles, these muon particle hit on the substrate, how do you know that exactly these particles are impacting? Maybe the other particles, because in nature, a lot of other particles are also available.
Okay. So your question is how to detect the tracks.
Yeah.
So by using optical microscope, we can achieve the submicron resolutions. The silver grains consist of the tracks less than 1 microns. So, for example, this image, so the grain by grain are separated in the 3 dimension in gelatin. So we can check grain by grain. So which grain is corresponds to the tracks.
Okay.
Okay.
Thanks.
Any more questions as far as from the internet? No, then thank you for Professor Morishima.
Thank you. Thanks so much.
And and let me give you some present. First of all,
Thank you.
every speaker of our colloquium receives
Thank you.
photo, not photo. So you'll see this is a plate for or
Thank you so much.
for Eugene Wigner. And also there is an explanation. And on the other hand, that is our presentation book. The author just left the room because it's a particular room combining fiction and science. So they are. So this is not only scientific, but also more entertaining.
Thank you.
And finally, some bottles of Hungarian wines. None of the favorite wine for this is the Tokai. This is yes. And this is the bottle of the best red wine of Hungary last year.
Thank you. Thanks so much. I like wine.
Yeah,
very much.
You should drink if you leave before or carry home, but it's up to you.
Tokai is very similar for us because our region is called Tokai.
Yes.
Tokai Chiho. You know Tokai Chiho.
Yes.
Nagoya is the Tokai Chiho in Japan.
Yes, but you don't have wine there. But it's not this kind, I guess. So anyway, thank you for coming and participating in the.
Thank you so much.
And giving the talk. So that's.
Thanks so much.